Okay. Okay, now the properties continuation. The complex number have these properties. If you have z1 plus z2, it's equal to z2 plus z1. It doesn't matter how it doesn't matter how you add them up. As far as you add them up, it doesn't matter the order. You can change the order. Also, z1 plus z2 plus z3 is exactly equal to z1 plus z2 first and then z3. Nothing changes. Okay, so this is the property. You will remember if you have z1 multiplying z2 plus z3, it's just nothing but the individual multiplication, the sum of the individual multiplications, which is z1 z2 plus z1 z3. Okay, so now if you get the complex conjugate of z plus and minus z1 plus and minus z2, okay, it is just z1 star minus and plus z2 star. So individually, you can take the complex conjugates of the complex numbers. This is how you do it. But if you get also the complex conjugate of the product, okay, it's just the product of complex conjugates of each one of those, okay, like that. And similarly, if you want to get z1 over z2 and the complex conjugate of it, it's nothing but z1 complex conjugate divided by z2 complex conjugate. Don't forget that the complex conjugate is z complex is equal to x minus iy if z is given by x plus iy. Okay, so this is generalized complex number and this is the complex conjugate of it. Okay, so when we are dealing with the complex numbers, we are actually using this kind of complex plane. This is called complex plane. We really have to know the properties of this plane. This is again x and y, but x happens to be just real part of z and this imaginary part of z. Imaginary part of z. Okay? So, for instance, this is 0, 0 again. So suppose that we would like to get z equals 1 plus I. As you see, the real part is 1. 1 is here. And then I is this 1 times I. So here, this is 1 again. This is just a point. So this complex number corresponds to a point on this plane. Okay? So we will see that there will be some complex functions which will give you some straight lines or curves and something like that. But in this case, it's just a point. Okay? So now there is some important properties of this thing. Okay, so for instance, z equals 2 minus 3y is just here, 2 there, and then 3y is 1, 2, 3. If you just get, it's just this point. So 2 minus 3y is just this point, okay? Just that point. So basically, the imaginary part is negative, but the real part is positive. If both of them are negative, then in this region, and if the real part is negative, but the imaginary part is positive, the point is going to be in that part of the plane. Okay, so now let's look at the geometrical properties of this. Okay, so this is xy, and now we have this point, some kind of point here, say this. Okay, so basically what happens is that this is x because this is x-axis, and this is y, okay, y, and this is r, okay, and this angle theta. So basically, r equals here is just square root of x squared plus y squared, okay, and theta equals arc tangent y over x. And sine theta is nothing but just y over r, and it is given as y over square root of x squared plus y squared, because this is the hypotenuse of this triangle. Cosine theta is given as x over r, but it is just x over square root of x squared plus y squared. Okay? So by using this, we can show that z equals z equals, which is x plus iy, it can be written as, since y is r sine theta and x is r cosine theta, it can be written as r cosine theta plus I sine theta. So this is z, right? So if you just, again, you're factoring out r from here. So this is just z as a function of angles. Okay, so but r also, this is very important, so we will use this often. And then r is nothing but the complex, the magnitude of z, which is just the square root of z times z star. So these are the geometrical properties of the complex numbers.